So good evening. So am I audible? Am I audible to you guys? Yeah. Hopefully, I think I'm audible to you all. So, welcome everyone. So, welcome to the week 2 of the aircraft propulsion course. So, this is a live session which we are carrying out for the second week. And so, in the second week, basically, we will be dealing with on aircraft propulsion, and the contents that were covered in week 2 includes the components of gas turbine power plant and gas turbine attachments, and we have introduction to various aircraft engines and their engine performance. So these were the topics that were covered in the week 2 session, and so this is a 2-hour session. So first hour I will try to briefly explain what was covered in the 2 lectures that were sent to you. Then in the next 1 hour we will try to solve some of the problems which we have. So we will start with the first session. So I hope I am audible. So we'll start with the lectures which were given on the gas turbine power plant. So basically we will be dealing with something called aircraft propulsion. So there are different engines that are used, but we are interested in the components of gas turbine power plant. So just right here. So you are interested in the components of gas turbine power plant. And as it's been explained by Professor, you have aircraft engines that work on gas turbine power plants, and you have land-based thermal electricity generation power plants that are used that also work on gas turbine power plants. So if we have a gas turbine power plant in which we have the basic components, so as discussed, the basic components where you had a compressor, then you have a combustion chamber, and you have a turbine. Now if in an ideal case, if you don't have the if you don't have the combustion chamber, in ideal case if you don't have it, then the energy difference across the turbine and compressor are the same, and you don't have any energy difference. That means the net work output, so I will write it here. So in ideal case, when you have only compressor and turbine, so the net work output will be equal to 0. So we don't have turbine and compressor as the components of gas turbine power plant. Instead, here the turbine and compressor, They are the rotary components of the gas turbine power plant. So in a combustion chamber, so you basically need an energy source for you. So you introduce something like called combustion chamber. So initially it was proposed to have a constant volume combustion. So that's why, because when you are having a constant volume combustion, it's better efficiency and was the main reason, and it was difficult to create initially this constant combustion, but eventually this specific arrangement with valves and all the associated arrangements of closing and opening of valves. So basically you had SI engines, the spark ignition engines and diesel engines with you before that. So people tried to use that as the combustion chamber where you have constant volume combustion, but then getting a valves and associated arrangements of closing and opening of valves was difficult. Then so this problem of making the combustion chamber, which eventually led to this gas turbine combustion, and that's what basically we are going to see now. So however, in a constant pressure combustion which we have, it has the convenience in the flow process. All the components of a gas turbine power plant are open systems, and it's a flow process. Hence, executing a constant pressure combustion is very good for when you have a high mass flow rate. So that's the main interest, and you need high thrust. So you need eventually high thrust means you need to make high flow of air flow rates through your systems. So in a general combustion or in a general gas turbine power plant, basically which we are mostly using for aircraft propulsion, you will have a compressor. So I will try to draw it here. So I will use some other. So you will have a compressor. Air will be coming in through this, and it will be compressing the air, and it will be going out to the combustion chamber. So the 1 to 2 process is what is usually referred. It usually is a isentropic compression process, preserving your entropy there. Then you have the combustion chamber where you try to do the heat addition process here. So you do the heat addition, and this is usually done in an isobaric condition, and from the outlet of the combustion chamber it will be going on to the turbine, where this is your exit of turbine, and here you have an expansion process where you take the work output, and from this expansion process this is also carried out in an isentropic process. So we assume that the heat is rejected to the atmosphere by the mass transfer to the atmosphere, and some mass is entering at low temperature to the compressor. So that's why it's an open system, you can say. And now, whereas if you see the standard SI and compression engines, so you can see that in a reciprocal engine we only have a piston arrangement. So if you ever seen, so you will have a piston, or so this will be cranked on to a crankshaft and all. Now this piston cylinder arrangement, the gas and the fuel injected into a cylinder, then the high pressure force on the fluid will exert force on the piston, and then the motion of will go out to the atmosphere. So unlike reciprocating engines, the gas turbine engines have separate components for separate processes. Here you have all the things being carried out by the single piston and the crank arrangement, but this is not the case for a gas turbine power plant. So for an open cycle gas turbine power plant, for an open cycle gas turbine power plant, you basically have a compressor, combustion chamber, then you have a turbine, and there are some limitations. We need to, since it's an open to atmosphere, you need to use very specific fuels, and more specifically it's for aircraft applications, you need very specific fuels to be used as it goes to the atmosphere. Now at the same time you have something called closed cycle gas turbine. gas turbine power plant you have. Now in the case of a closed cycle gas turbine power plant, you have a compressor, and this goes on to an heat exchanger, and then this comes on to a turbine. Now from the turbine, since it's a closed thing, you again have a heat exchanger process, and this again comes back to cold thing will come back to your turbine. So here the heat exchanger process will have your thing, and this you can keep it as a single set, and this some amount will be taken by this and it will go out, it will come here and it will take the heat and it will go out. Now so here this is the heat exchanger, and so this will heat the thing. 2 is the first state and this comes to 4. Then you have the exit of turbine, that is the 4. From the exit of turbine you again pre-cool it using a pre-cooler, where it takes, so this arrangement will take out the heat from the heat exchanger, and then the cooled thing will be going on to the compressor. So advantage of this closed cycle gas turbine is any fuel, solid fuels which are generally used can be used here, because it's a closed cycle. Now it's not open to that much, and we can have external combustion, that is gases which are combusting would not pass through the turbine or involved in any of the doing the work, and so this is an external combustion, while in open cycle this was an internal combustion, because everything is happening inside the combustion chamber. And so in open cycle the fixed working fluid is fixed, it's an air is your working fluid. So these are some of the important points that you need to remember. And in closed cycle we can have any fuel for the same working fluid is passed in the circle, and we have a choice of working fluid because now it's not open pressure, so you have a choice. And single shaft arrangement of gas turbine power plant is good, and for a fixed load, that is for the case of a closed cycle gas turbine power plant, the single shaft arrangement is good for a fixed load and fixed speed application. Like when you have a base load power generation, you need to constantly generate a particular amount of power every time. So that in those cases closed cycle gas turbine power plants are more effective. Now if you see the comparison thing, for a closed cycle gas turbine power plant, we can change the pressure in the circuit and control the output of the power plant, and we can use any fuel, that was as I mentioned, and we can opt for any working fluid with good heat transfer characteristics for a closed cycle. And the upper limit of temperature at the entry of the turbine, it depends on the how much. So now you have heat exchangers in before that, so you need to critically design the heat exchangers properly for this thing. And there are some of the properties of fluid that needs to be maintained. So there are some properties of fluid, so I will just name them, some of them. So one thing is this fluid needs to be cheap, and then it needs to be readily available for your use, since you will be using it for large quantities for large numbers, and within a single day itself you will be using it for large amounts. And it should not be explosive or corrosive. So I am not writing here, but I am just naming. And it should be non-toxic, and it should be non-inflammable, and it should have good thermal conductivity, and it should have high specific heat. And gamma value, that is the ratio of specific heat should be high as possible. Now said this, if you now look at the gas turbine attachments that was discussed by Professor, there are some of the gas turbine attachments which makes the system more efficient and all. Out of that, the first important one is the multi-stage compression. So this is one of the important process. So in a multi-stage compression, so if you draw the thing, you will see that you have a compressor, then this compressed thing will go on to a high pressure compressor will come. So this is like a low pressure compressor, then you have a high pressure compressor, the exit of this will be going to the combustion chamber, and from there it will be coming on to the turbine. And you have turbine 1, which is a high pressure turbine, because at the outlet you will have a high pressure. From this high pressure turbine you will have once expanded, you will have a little lower pressure. So this will go to the turbine 2, where it is a low pressure turbine. Now this multi-staging, if you see, the high pressure compressor is combined to the high pressure turbine, and this high pressure turbine runs the high pressure compressor, and this low pressure turbine corresponds to the low pressure turbine here. So the multi-stage compression is desirable to raise the overall pressure ratio of the gas turbine power plant. So that's the main interest here, why we are using multi-stage. And then now it becomes critical, the blade design and all of the compressors and all will become critical once you start doing the multi-stage compression. And another thing what people try to do is, you have gas turbine with heat exchanger. So when you are seeing gas turbine with heat exchanger, here also, so you have a compressor where you have inlet coming, then you have a heat exchanger to raise the temperature. So then you should have something that takes out the heat. Then this system goes to the combustion chamber, then it comes on to the turbine. So this outlet of the turbine is what you can take. It can be used for, again, using within the heat exchanger itself you can use it. Now for an open cycle with heat exchanger, it is not going to increase the work output, because in an ideal case the pressure loss in the process of heat exchanger is, it's not so high, and we can get combustion starting at the temperature which is the temperature near to the combustion chamber. So here before this you can increase your temperature. So that's one thing why we use the heat exchangers. So then if you are elevating, so now basically you are elevating the temperature of the combustion. So from the basic thermodynamic process, if you are adding heat at high temperature, the efficiency of the cycle will also increase. So that's why, so when in the future classes you will see that you will be drawing the PV and TS diagram for this kind of multi-stage compression and all. You will see that when you are taking the elevated temperatures, the net area within the curved region within the PV diagram and all, you will be seeing it is more. So the net efficiency of the cycle also increases when you are heating the air from the outlet of the compressor. So the heat exchanger arrangement is used for at low operating pressure ratios of the cycle, since this has lot of friction losses, because now you are sending it through heat exchangers and all. So it eventually reduces the net work output due to these other losses that are present when you are adding extra heat exchangers and all. Now, and another arrangement, so these are different attachments that are given to a basic. So basic gas turbine power plant will have a compressor, combustion chamber and a turbine. Now you need to increase the efficiency because your power loads and the working loads are heavier, demands will ask you for more things. So at that times you need to make your system efficient. So at those conditions you will be using these kind of attachments. And here you can have one more thing, like you can have a open cycle gas turbine with external combustion. So here also not a big change, but you have a compressor, then you have a heat exchanger, then this goes to the turbine, and from the turbine exit you have the fuel positioned here, and this undergoes the combustion, and this heat can be used in the heat exchanger. So you have the one over here. So we can have, so in this the advantage is we can have solid fuels like pulverized coal and all, you can have to heat the, which can be used in the heat exchanger, and we can use fuels which can cause erosion, or because these are not directly coming into play with the turbine, so you can use any of these fuels. And this arrangement is suitable mainly for electricity generation, where you have a prime mover, which like the turbine which moves and you take the shaft power output and you generate the electricity. So those places, this kind of open cycle with external combustion is more useful. Now one more attachment that you can add to your current system is you can add something like called intercooler and reheater. So these are the two additional attachments that you can add. So where it is added is like you have a compressor, then you have a intercooler where after when it passes through the intercooler, so here the air comes, you have a low pressure compressor, then it passes on to this intercooler where it gets cooled down, and then it goes to a high pressure compressor. From this high pressure compressor you have a heat exchanger again, that then you heat it up and then you go to the combustion chamber, then you have a turbine to extract the energy, and then this turbine exit you can again reheat it, where this will again undergo an expansion process, and with this thing you will have a heat exchanger over here. So this heat you can reuse. That once you are reusing, that means you are making your system more efficient. So this is you have low pressure turbine and you have a high pressure turbine. And now, so what is the advantage over here is when you reduce the temperature of air using an intercooler, as you know that a process of compression is achieved at the isothermal state, then the isothermal compression has minimum work output. So when you are having an isothermal compression, the work output or the net work input to the system will be minimum. So objective of an intercooler is to reduce the work input in the process of compression, and then it will go to the combustion chamber. Before that we will get heated it up by the heat exchanger which we have here. And the heat exchanger objective is to increase the efficiency of the cycle. Then the air will go to the high pressure turbine, after which it will get heated up by an external heater or by a combustion source called the preheater, we say. This reheater will reheat up, and here the objective is to increase the power output to the cycle, increase the power output of the cycle. Then after reheating, it will go to the low pressure turbine, and this low pressure turbine gas will go to the heat exchanger and it will be exhausted to the atmosphere. So basically this is an open cycle with different attachments that we have introduced. Now once attachments you have seen, then there are ways through which you can keep your arrangement, that is how the coupling between the turbine and the compressor is, that you can change. So there are different arrangements for that. So out of that, the first one is twin shaft arrangement. So in a twin shaft arrangement, this is basic thing, you know, you have a compressor, then you have a combustion chamber, then this goes to the turbine. From the turbine you and again have one more turbine. From this you take the output. So this is like a power turbine or a free turbine, and here you have the inlet, that is at 1, then you have 2, outlet is 3, then this outlet will be 4. Now why we need a twin shaft arrangement is like, in a single shaft is good when you have a fixed load at fixed speed applications, but this is not the case every time. You need variable speeds and all, so you need flexible speed and flexible load conditions. So for that, where some applications are like marine propeller and pipeline compressors, you can see these kind of applications. So you have some, so this particular region, that is this combustion chamber, compressor and turbine, is what is usually referred as a gas generator. And now we don't need any gear base to connect to these compressors and all, but since we have a gas generator, we need to provide a we need to have a simple starting mechanism we can have. without doing any much work. That's one advantage of this gas generator. And only thing you need to add more is like you need to have a control mechanism. A control mechanism is required for this kind of twin shaft arrangement. So since any decrease of load will increase the speed of the turbine, and then the speed needs to be controlled. So if you have any load changes here, the net effect will be seen on this power turbine. So you need to control this power turbine. So for that you need some controlling mechanisms will be more prompt for you. Now apart from this kind of twin shaft arrangements, you can have something called multi-spool arrangement. So if you guys have any questions, you can just stop me or you can ask. Yeah, so in a multi-spool arrangement, so we have a, so why we use a multi-spool arrangement is we need a high compression ratio. So in case of gas turbine power plants, multiple compressors can be used and multiple stage compression can be done. So one way of doing this multi-spool arrangement is like you have a compressor, then this is will again go to one more compressor over here, then the outlet of this goes to the combustion chamber, then the outlet of this comes to the then the outlet of this comes to the low pressure high pressure turbine, and then this comes back again to a low pressure turbine. So now if you see, this high pressure turbine will be connected to the high pressure compressor, whereas this low pressure turbine will be connected to the low pressure compressor. So this kind of multi-spooling, so there you can have a separate control, speed control over the high pressure compressor and high pressure turbine, how much percentage it needs to be controlled, and low pressure turbine and low pressure compressor is coupled now, so you can vary according to the speeds according to the requirement. So arrangement is useful to achieve higher pressure ratios which are required for gas turbine power plants, and we mechanically separate the compressors and turbines, and hence you can have different speeds. So that's the main requirement which we have when you are using a multi-spool arrangement. Within this multi-spool itself, there was one more small classification that was mentioned. It was like, it's called 3-spool arrangement. So in a 3-spool arrangement, so basically you have a propeller, then this propeller is connected to a low pressure compressor. So the propeller can also now provide a more robust thrust here, then it goes to high pressure compressor, and this high pressure compressor is now connected to a high pressure turbine. Okay, before that you have a combustion chamber, from that it goes to the turbine where it is high pressure turbine you have. From this high pressure turbine again it goes to an intermediate, so turbine should be having, it's expanding, so your net volume will be increasing. So you have an intermediate pressure turbine, then this again goes to a low pressure turbine. Now this propeller can be run using the low pressure turbine, so its slow motion can give you the propeller the required thing, and this high pressure compressor and high pressure turbine can move with different speeds, and you have the intermediate, these things which can be connected to the low pressure compressor. So this kind of 3-spool arrangement is what it's called, and this 3-spool arrangement is necessary for to decouple different speeds. If you want different speeds for your system, then you can use this mechanism and you can decouple each separately. If you remove the high pressure compressor and high pressure turbine shaft power output, then you can vary your system at the low speeds and all. So this is the major advantage. And so propeller would run at a speed which will be catered by the low pressure turbine and low pressure compressor once you are removing them. And so that's the advantage of using these kind of systems. Then one more thing that was introduced to you was called combined gas turbine and steam power plant. So here the main goal was like this combination is used to recover the heat rejected and to increase the overall efficiency of the system. So that's the major goal. So here when you are using a combined gas turbine and steam power plant, so you need to have a compressor that basically you know. Then you have a combustion chamber, and at the outlet you have a turbine. But now at the exit of the turbine, so you have a gearbox here. So basically in aircraft engines you use gearboxes to connect your body to the engine things and all. Now this gearbox will be connected to the generator. From this it will be connected on to the steam turbine. So generator will get the heat and it will run the steam turbine. Then from this steam turbine it will go on to the condenser unit where it will condense. Then you have a pump to pump this condensed liquid on back to a, so here you have the steam generator. It can act as more number of systems. So here from this heat generator this steam will be coming on to this to run the steam turbine. Now the exit of the turbine can go into the steam turbine and it can heat the liquid or the water that is present there to get the steam out. So you have what you have done is you have combined the output from the gas turbine and now you are using it for heat rejected is being used to heat the steam and get more work output from the system. So that's the advantage of using a combined gas turbine and a power plant and steam power plant. So this is not usually applicable only for aircraft propulsion, but you can use it for land-based gas turbine engines. You can use that. Now the basic difference between this kind of steam power plant and gas turbine power plant is like steam power plant the water is your working fluid, whereas for gas turbine power plant you have air as your working fluid. And in the steam power plant your water will be converting it into steam, so there is a phase change, whereas in gas turbine you don't have any phase change. And for steam power plant you have very high pressure ratios, whereas for gas turbine power plants relatively you have a lower pressure ratios. And steam power plant, as we have discussed in the last sessions, you have Rankine cycle as your working operational cycle, whereas for gas turbine engines you use Brayton cycle. And the net thermal efficiency is higher when you are considering a steam power plant, whereas it is comparatively lesser for a gas turbine power plant because the thermal heat taking and reusing is more there. And the net work output, it all includes the pump work and all for steam power plants, but you don't have that much. You only have a compressor and a turbine when you are considering a gas turbine power plant. So that reduces the number of rotary parts and all the losses when you are considering a gas turbine power plant. And the net work ratio, so how much work being done, is high for a steam power plant, whereas it is comparatively less for gas turbine. And important thing is in the steam power plants you have external combustion, whereas for gas turbines you have an internal combustion. Steam power plants basically are used for electricity generation and all these purposes, whereas gas turbine, as you know, it's used for mostly for aircraft propulsion. Now say these differences, these are just I am just briefly explaining what was just taught to you, so that you can just remember that. And apart from gas turbine and steam power plant engines, you were introduced to something called reciprocating engines, where the reciprocating engines is the back and forth motion is happening, and major advantage of using such reciprocating engines is the, I'll just write it out here, the reciprocating engines was introduced to you, and major advantage is like it's the lower mechanical efficiency due to the higher friction losses is there, but balancing in these kind of reciprocating engines is critical and overall efficiency is higher. That's the advantage when you are using a reciprocating engine, and the maximum temperature that can be used in the reciprocating engine is higher because you don't have the constraint of turbine blades and all in reciprocating engine, but you have these constraints in when you are going into a gas turbine power plant, and there is a way higher weight per kilowatt when you are considering a reciprocating engine. Eventually, when weight is higher, your cost of operation is also higher, and you can cooling and lubrication is all easier when you are cooling is comparatively simple in a reciprocating engine, but lubrication and all you need to keep on doing that, else the frictional losses will be more if you are not properly maintaining the reciprocating engines. So this was one part of the session that was covered in the lecture, 2 sessions that were given to you, and the other part that was covered was regarding the aircraft engines and their engine performance. So once you know how an aircraft, what are the basic components of an aircraft, then how different attachments can give you more efficiency and more work output, and how to regulate the speeds and according to your requirements. That's very important, because when as an aerospace engineer you will be asked to, where you have an aircraft that needs to take off, that need to cruise at a higher altitudes, then it needs to come down, and so all these cases you have different speed requirements, so you need to catch up on all these speeds. So as an engineer you will be looking onto all these kind of attachments to get different speed conditions and all. Now once you know these engines and there are different components to it, now you need to know the engine performance parameters. So we will go on to the next this thing called engine performance parameters. So till now any questions are? Okay. So now once if you see the engine performance parameters, there are certain number of things that are very important when you are mentioning your engine and all. So the first one in that is the thrust. So this is an important term when you are using an aircraft propulsion. Anyway, thrust is the main thing, that's what basically we are using all these kind of stuffs. So if you say you have the body of the system and you have a black box which does all the work within the system. So basically you have an aircraft and you have some amount of air that is coming in through the blade, through the 2 engines that are mounted on the wings that you might have seen. So say that is the velocity of the incoming air is CA and the pressure that which the air is entering is PA. Now this air will be coming out after some operations are carried out, the net amount will be thrown out to the atmosphere. Now say that coming out is at a velocity Cj, that's the jet velocity, and it is coming out at a pressure Pj if we consider. So this is coming out through through a particular area outlet which is Aj if you consider. So say the net air flow rate is m dot A, that is into the system. Then the thrust is nothing but change in momentum. So this is the important thing. Now change in momentum is nothing but you have the rate into the velocity. So the velocity is the outlet velocity, jet velocity outlet, minus m dot A into the input. So it's nothing but m dot A into Cj minus Ca will give you the thrust produced by the engine. And if we consider, so here we considered in this condition we consider the exit Pj is equal to Pa. that is, it is giving the jet is coming out to the atmospheric pressure itself we are considering. So we didn't have any pressure term. Once you add this pressure term also, then the net thrust, which is represented by T, it is nothing but m dot A into Cj minus Ca, plus the net thrust is nothing but, you have at the exit you have a nozzle, and this has a area of Aj Vz. So thrust is nothing but force per unit area. So what we are interested in here is how much, sorry, pressure is nothing but, okay, one second, I will just, so pressure is nothing but the net force, normal force acting on a system to the area, normal cross-sectional area. Now you are interested in the thrust force that is acting, so it is nothing but pressure into area. So it is nothing but the area of the exit at the nozzle into the pressure. So pressure, you have a difference is Pj minus Pa is the net change in pressure, that is usually taken into account. So now these are the basic definitions of thrust when you are having an aircraft engine, and what is the basic thrust. If thrust equation, if someone uses, you can use these equations. Now once you know thrust, then you will be asked about what is thrust power. Thrust power is nothing but the thrust into the.
Hello, sir.
Yeah, yes.
Hello.
Yes, Ramachandra. Yes, you are audible, please.
Sir.
Yes. I can hear.
Where will the pressure will be here, sir? At the exit or inlet of the engine, sir?
No, so pressure, when you are having a pressure component, usually the exit of the nozzle is also been sent out to the atmosphere. So usually Pj is also usually equal to Pa, but when you are having a rocket engine, so it's a vertical thing. Now your pressure at the exit changes with the altitude. So at that time the pressure components become more important when you are writing the thrust equation for a rocket engines and all. When you are using an aircraft engine, the aircraft engines are basically designed for a cruise conditions. That's like you take off, then you have a cruise condition, then you land down. So you should be staying more time in the cruise conditions. So they are designed for these kind of cruise conditions. So at that time the pressure, since you are having a air that is coming in, you have a compressor that compresses it to a very high pressure, then it is undergoing combustion, then it is turbine will take you, expand it, and you will have a low pressure that is coming on. Basically when you are throwing it out to the atmosphere, eventually the system will merge out to be nearly to atmospheric pressure itself. Only when you are having a supersonic and all conditions, this pressure matters. Apart from that, in a real aircraft engines, normal commercial aircraft, you can say this exit pressure is approximately equal to the atmospheric pressure. If pressure changes are there, this you can see at the exit. And if your question was where the pressure acts on an aircraft engine, then you should see that whenever your engine is undergoing a combustion, now when combustion is happening, your aircraft body should be moving forward. It's not like the engine is working and it's producing some thrust, but your aircraft frame also should be going with it. So the net thrust or the pressure that is acting on the where it is getting connected is the gearbox, or so you have a coupling like thing. So that gearbox will connect the aircraft body to your engine, and that's the area where the pressure total net thrust acts. So this makes the aircraft to move forward. Is that clear? Well, I hope I answered your question.
It's clear.
Yeah.
Yes, sir.
Yeah. So now once you know thrust, then you need to know what is thrust power. So thrust power is nothing but you have a thrust into the velocity of the aircraft. So the thrust is nothing but, so here we are considering Pj equal to Pa for now. In that case, you have the net airflow rate into the velocity change into the aircraft velocity. So Ca is the net air coming in, if you are considering, so if you know something like wind tunnel, even if the body is stationary and you send the air, or air is stationary and you send the airplane, both are the same velocities. So you take CA as the air velocity, that is nothing but the aircraft speed that you are considering. Since you can't do experiments with such high amount of air, what we do is, you can't make the lab scale models to go at that high speeds. So you have the wind tunnel experiments where you push the air at those speeds, keeping your aircraft, the specimen which you are interested in, at a particular location, and you send the air at that CA velocities. So that's one thing people do. So once you know thrust and thrust power, now you need to introduce something called propulsive efficiency, and this term is important because the propulsive efficiency is important for any of your system. So it is nothing but the thrust power that is generated to the change in kinetic energy. So in those case, okay, I will not do the derivation. The final equation that you will come down to is nothing but 2 by 1 plus Cj by Ca. So this is the equation for the propulsive efficiency that was derived. Now if you see here, if your Cj, the velocity of air, if it is equal to 0, that is in the static conditions, if you see, if it is 0, then your propulsive efficiency goes to 0, because Cj by Ca, so 1 by 0 is infinity, and 1 by infinity eventually goes to 0. Whereas if your velocity Cj is equal to Ca, then your propulsive efficiency goes to Cj and Ca goes off, and by 2 you will get 1. So these are ideal conditions. Propulsive, if Cj equal to Ca, that means you don't have any thrust being acting on that, but you will have the maximum propulsive efficiency. And another term that you need to be interested is something called energy conversion efficiency. And here also the energy conversion efficiency is nothing but change in kinetic energy by the input fuel energy. So the final energy equation that you will boil down to is something like 1 by 2 air by fuel ratio and times the square of velocity difference by the calorific value. So this is the equation that you will come down to. And so calorific value, I hope you know, this is the amount of energy liberated when you have a unit kg of fuel being burnt. So now once you know what is energy conversion efficiency, then the overall efficiency is what you need to know. And overall efficiency is nothing but you have your propulsive efficiency times the energy conversion efficiency is what. And this, if you write in terms of equation, it's nothing but your thrust power divided by the input fuel energy. So basically you have a fuel. From this fuel you use the energy and you increase the kinetic energy of the system, and you use this kinetic energy and make the thrust power. Now the energy that is from the kinetic energy to thrust power, when you go, it's called the propulsive efficiency. And when you go from fuel to the kinetic energy when you are traveling, it's the energy conversion efficiency. And from the fuel to the thrust power, when you are saying, this is the overall efficiency of the system. So I hope this representation is very easy for you to understand what actually these things mean. And now,
Sir,
yes.
sir, can you go back to propulsive efficiency?
Yes.
There, in case 2, you TJ 1.
Yes. Yeah, in case 2, Cj equal to Ca. So at that time propulsive efficiency comes to 1. Yeah.
Then it is 100% efficient, sir.
Yeah.
Then how the thrust will be produced, sir?
Yes, it's an ideal condition. You will never have a engine with such high propulsive efficiencies and all. Usually you will be having some propulsion 60 to 70% is what you try to maintain, and you will not have this. If you are having this thing, then your net thrust is 0. So you will never have an engine with this kind of high propulsive efficiencies. So it's absolutely correct what you said.
So in that case, thrust is 0, sir.
So when you are having this kind of thing, so your jet velocity is equal to your air velocity. So there is nothing that, so your thrust equation says m dot a into Cj minus Ca. Now your Cj is equal to Ca. That means thrust is equal to 0. So eventually there is no thrust. So your airplane will not move forward. But you will never trade.
If you don't have thrust, then propulsive efficiency need to go to 0, no, sir. Then how it will be 100%?
No. So propulsive efficiency is like, that is the thrust power that is generated per kinetic energy change. That will go to very high values, because the whole thing, the total kinetic energy change is not going now to the thrust power. So if you see the total kinetic energy change is now going to very high values, because the total energy that you are supplied is now going into taking from Cj to Ca it is going. At that time the downstream, that is the denominator value, goes to very high value, and then your propulsive efficiency will go to very high. Sorry, it's inversely proportional. So it will go to 1. So if from the equations itself you can see, if you are having this Cj and Ca values, and if it is equal, this net value will turn to 1. Is it clear or still there? Yeah, Ramchandra, is it clear?
Yes, it's clear, sir. You can move on.
Yeah. Yeah, so once we introduced that and we saw how the propulsive and all efficiencies are related, then so the net, say you have the thermal efficiency for your case, then the thermal efficiency is nothing but the net work output to the heat input that is being supplied, and thrust is nothing but m dot a into Cj minus Ca. So now if you want to increase your thrust, there are two ways. Either you can increase your net velocity change, keeping your m dot a changes constant, or you can either increase your m dot a, keeping the Cj minus Ca small. So there is a up and down thing you need to. If you are putting a more amount of air and fuel, then you should compromise on the velocity thing, or either you should compromise on the velocity thing and you should increase more amount of air that you need to be supplied. So based on how m dot a, if you are changing, there are certain aircrafts, and if your velocity change you are changing, based on that you have certain different variety of aircraft that work on both principles. We will look into that soon. And then there are some other terms called specific fuel consumption. This is nothing but the fuel mass flow rate divided by the thrust that you have produced. So this is nothing but, it will come down to fuel by air ratio times 1 by tau, and this tau is nothing but your specific thrust. So specific thrust is an important term. That is nothing but the thrust per unit mass flow rate, per mass flow rate of the air that you are supplying. So specific thrust is also one important term. Now if you introduce this fuel air ratio also into the system, so the net thrust equation, now you can just modify a little bit. It will be nothing but, you have the m dot a, only thing is you will now have the air to fuel ratio that needs to be accounted before your velocity change, and then remaining part remains the same, that you have the pressure and the pressure component remaining the same thing. Now there is one more thing called takeoff thrust. So it's like, it's called, also called as static thrust. So you have takeoff thrust. So it's also called static thrust, and is that thrust is actually obtained at very low speeds or static conditions of the engine. So that's the thing. And then the thrust is basically upon, so the takeoff thrust is nothing but thrust by mass flow rate of air. And if you see, for a given fuel by air ratio that tends to 0, then you have, say, the atmospheric pressure and the jet exit pressure is nearly same, and the static, under static conditions you can say the velocity of aircraft remains 0, near to 0. Then if you substitute here in the first equation, you will be remaining with only one term, that is Cj, that is the jet velocity. So now if you do the mathematics and all, finally you will come to some equation called like thrust is nothing but 2 times the energy conversion efficiency into your calorific value times the mass flow rate of fuel by the net jet velocity. So here if you see, your this efficiency is and the fuel used, it is dependent on this energy conversion efficiency. The thrust is dependent on your energy conversion efficiency and the fuel used. At the same time, the fuel flow rate is inversely proportional to the jet velocity. So if we handle more mass flow rate, then we will have smaller jet velocity that we have if you are considering the static thrust. So that means if you have smaller jet velocity, then you have more mass flow rate of fuel, and you can have more amount of static thrust. So that's the key thing there. And one more important thing is the aircraft range. So if you have a given, so this is what determines the commercial viability of an aircraft and how much fuel you need for moving into a particular distance. So it's the distance that is traveled from one place to another for a given amount of fuel. So that aircraft range is also important when you are considering a commercial flight and all. And so for finding the equation for aircraft range, it is there in the lecture, so I will not derive all the thing. Mostly aircraft are designed mostly for the cruise conditions. So you will have if you have the aircraft that is there and you have weight that is coming here, then you have something called lift that makes your system low, and then you have thrust and you have drag. So in the cruise conditions you have all these things being matched. So that's why lift is equal to weight you consider when you are cruise condition, and thrust is equal to drag you consider. So this is the condition why at cruise conditions you see this. And the range, the aircraft range, final equation will be like, you have the L by lift by drag log times the ratio of in fuels times the thrust specific fuel consumption whole inverse into the velocity of air by the gravity. Now this thrust specific fuel consumption is nothing but fuel flow rate by the net thrust acting. So from this equation you can see, for a given aircraft speed, that is Ca, the range will decrease, that is S will decrease if your net thrust specific fuel consumption is more. So lesser your range when you are having more, we are consuming more fuel for a given for a given thrust you are consuming more fuel, then eventually your aircraft range will be decreasing. Apart from this, you have some other, so from all these things, from using this engine performance and engine parameters, you have different engines that work on all these different principles. So one of the first thing that was seen was something called piston engine. So you have a propeller and you have a piston engine here. So the thrust is produced by the propeller, that is you have here, and it is suitable for low altitudes It is suitable for low altitudes and cannot be used for high thrust applications, since those thrust conditions and the weight of the piston increases, and the engine also cannot handle large amount of mass flow rates in this kind of piston engine arrangements. Then you have something called turbo prop engine. Now in a turboprop engine you have a propeller, then you have a compressor down for you, then you have a combustion chamber, then you have a turbine. From this turbine this goes on to the nozzle. So nozzle will provide the required velocity for the jet to move out faster. And so at this high speed application, so turboprop engines can be used at high speed applications. The propulsive efficiency of the aircraft is high, but further noise of the propeller becomes an issue, and it needs to have a special design for the propeller, because at the propeller tip you can have Mach going to 1 and you can have a lot more losses when you are going at higher altitudes and higher speeds. So that's a limitation for turboprop engines. So they are not generally used for such high speed applications due to this constraint on the blade tip problem, and they are used for with 3 spool arrangements. All people try to use it. So that's basically used for a turboprop. What the limitation is for a turboprop. People used to have the turboprop engines, but for a low altitudes you can use these things. Now when another thing that came out was something called turbofan engines. Turbofan engines, only thing is propeller is changed to a fan and you have compressor remaining, since things remain same. You have a compressor, you have a combustion chamber, then you have a turbine, then you have a nozzle. Those things remain same. Now additional thing is some air will be coming into the compressor and it will go to the combustion chamber. Apart from that, some air will come to the fan and it will go out in the, and it will be taken as a bypass air, and both this bypassed air and the air that is going into the combustion chamber, both will now add up into the thrust formation. So that will give more thrust values for your system, and these are used for moderate altitudes and for moderate speeds. Up to moderate speeds you can use these turbofan engines. And another thing, engines is something called turbojet engines. Here there's not big change. Here instead of fan you will have this diffuser and you will have the compressor sitting over. Remaining things all remain the same, and you don't have any propeller, and the thrust through the jet engine, through the jet exit only you will have from the nozzle. Water is coming, that is the jet exit, and that is the only source for the thrust. And these are used for high altitudes and for very high speed applications. Turbojet engines are used mostly for military and applications. We use turbojet engines. Now it can go to high supersonic speeds and all. Now these are like engines that work on up to a Mach number of 1 and 1 less, near to 1 and all. But once the commercial aircraft, they work very close to 0.3 to 0.6 ranges, whereas now you want missiles and all which needs to go at very high speeds and all. There are engines called ramjet engines. Ramjet and scramjet engines are there. So these go at very high speeds, and only change is that you don't have any compressor or turbine which has a rotary parts which reduce your efficiency and all. Instead you have a ram effect where your inlet momentum of the air itself is used, because you need to move your ramjet to such high velocities such that the inlet air, when it comes through the diffuser, it will eventually be compressed and it will avoid. So this avoids the requirement of compressor and turbine for getting the thrust. And so this inlet air, now it will be coming into the combustor and you will be injecting fuel over here, and this will get combustion. And problem is like when you are having such high speeds, stabilizing of the flame inside the combustion chamber is very difficult, because your flame will also blow off, and if flame blows off at such high altitudes, you need to come down at lower altitudes to reignite, and that's a issue when you are having a missile and all. So you need to have engines, you need to hold the flame at that positions, for which people use something like V gutters and all, where they are called flame stabilization things, where you can hold the flame for long time. So that's one thing that ramjets are used for, where very high speed applications they are used for. Then one more additional thing was prop fan or unducted fan. Those are general usage things. Just okay, I will not just describe that, but I will just finish that by saying that the order of increase of speed of aircraft, if you see, piston prop, then you have turbo prop engine, then you have turbo fan engines, then you have turbo jet engines, then you have ramjet. So this is the increasing speed of the aircraft and jet exit velocities. And if you see, this is the, so this you can put like this, and there is a decrease in the mass of air as you go to ramjet engines. There is a decrease in the mass of air that is handled, that is also there. And there are different regions and all that is been classified in the lectures that you might have seen, but eventually this will be dealt in further lectures also, so I will not try to explain what are those things. Only finally I will just explain what the final graph that was given in the last lecture. So this was the plot between the propulsive efficiency and the speed of aircraft. So you saw that for a turboprop it goes and then comes down, whereas for turbojets and turbofans with low bypass and high bypass, when you are increasing your net thrust, propulsive thing increases, whereas low bypass, there is less amount of air that bypasses from the fan, so you will have a lesser propulsive efficiency for a given speed. So that's the graph, and you will have similar more graphs being introduced when you are going on to the subsequent lectures. You will see that. So this is what I will wanted to just briefly explain what was the things that was taught to you in the previous two lectures. So are there any questions? If not, we will move on to the questions that I have. So we will move to the first question. Yeah, so the question is, so the question is, multi-stage compressors are used for, and the options are like raising pressure ratio of the cycle, increasing the plant work output, increasing heat transfer, or reducing work input to the cycle. Are there any suggestions or someone answer for this?
Rising pressure ratio of the cycle.
Yes. So the multi-stage compressors are used for raising the pressure ratio of the cycle. So remaining options, if you see, increasing the plant work output or heat transfer or reducing the work input to the cycle, those are not in any way related to multi-staging. Those all reduces your efficiency. So you don't. So that's why that's not the correct answers. Now the second question is, consider the following statements and select the correct one. So steam power plant runs on Brayton cycle. Steam power plants have higher pressure ratios than gas turbine power plants. Thermal efficiency of gas turbine power plant is less than the steam turbine power plants, and the working fluid in gas turbine undergoes phase change. So the question is, choose the correct one. Are there any guesses? Yeah, I think we have discussed this. I have just orally mentioned, and in the lectures this was mentioned. The question was, Okay, choose the correct one. Does anyone have any suggestion?
Sir, option D is
Okay, so you are saying option D. So if you look into the option D, the working fluid of gas turbine undergoes phase change. So if you look into the gas turbine, you have a compressor, you have a combustion chamber, then you have a turbine. So inlet is air. So if you look, gas turbine is used for aircraft application. So you just think of an aircraft, you have an air as an inlet to the turbine. So you might have seen on the wings you have two engines that are mounted onto the wings, and you have air that is being sucked up by the engine, and that air goes on to the combustion chamber, and that air is what expands the and turbine runs, and it is sent out. So there is no phase change that is happening. So by phase change means there is a change in the state of the system. Either it changes from a fluid to a vapor condition, or solid to liquid, or liquid to vapor, or either case directly from solid to vapor condition. Such phase change are happening is what phase change means. Yeah, Sanskar, what we were saying? Yes, option B is the correct one. Yeah, Ramchan. So I hope you understood why D is not the correct one.
So thermal efficiency of the gas turbine.
Yeah, but as I mentioned, I think in the lectures of that one, the thermal efficiency of steam power plant is less. It is saying that gas turbine power plant is less than that of the steam power plant, but actually the thermal efficiency is comparatively high for gas turbine power plants. That's, I think in the lectures it is mentioned why it is. Okay, just not put a tick here. Yeah. So the actual correct answer is the steam power plants have higher pressure ratios than the gas turbine power plants, because they work at very high pressure ratios. These steam power plants, they work with high pressure ratios than the gas turbine power plants, because they are land based.
Sir,
Yes. Yes.
combustion chamber we are adding some amount of fuel, no sir?
Yes, you are adding fuel.
I'm saying, did we? Then it's kind of phase change, no sir?
No, so here the working fluid is not the fuel. The working fluid is air. If it was asked any phase change, you would have added the fuel that is getting evaporated and getting combustion. But here the working fluid in a gas turbine engine is your air. So that's what you use as a working fluid. Fuel you use for just adding more heat to the system to get more efficiency to run the turbine and all. But basic thing is air that you are using. Is it clear?
Nice.
Yeah. So if we go to the next question. So here I think your question may be answered. So third question is, only rockets can be propelled to space because they have high propulsive efficiency. They can work on different types of fuels. They are not air breathing engines. They can generate very high thrust. So any guesses why rockets are only used for using space missions and all, not aircrafts?
Not an air breathing engine.
Yes. So rockets are not air breathing engines, and so when you are going, as you are increasing your altitudes, the pressures will be decreasing, your temperatures will also be coming down, and the availability of air for taking it as an fuel. So basically you know that for getting an ignition you need to satisfy the triangle. That is, you need to have a heat source, you need to have a fuel, and you need to have an oxidizer. And when you are going to higher altitudes and you are going to space, outer space, you don't have any atmosphere. So eventually you are not having any air present over there. So I think here, yeah. So the answer is it's not an air breathing engine. So that's why rockets are
They
used.
can also generate higher thrust also.
They can have higher thrust, but the question is why only rockets can be used propelled to space. If propels rockets and what are the conditions under which rockets are, they can have higher propulsive efficiency and all. But then here the only condition why mostly you are choosing is because they are not air breathing engines. I hope that is clear. So we'll go to the next question. So next question is, in a turbojet engine, so it's mentioned turbojet engine, the combustion products after passing through the gas turbine are discharged into: one, it is discharged to a vacuum; second, it's discharged to a atmosphere, or it's discharged back to the compressor, and or it's discharged through the nozzle.
Discharge through nozzle.
Yes. So in a gas turbine combustion, we have seen this thing. You have a combustion compressor, you have a combustion chamber, you have a turbine, and this turbine exit, it goes on to the nozzle, and this nozzle, through this nozzle exit, it is discharged out to the atmosphere. So the combustion products after passing on through the gas turbine, they are passed on to the nozzle. So I hope that is clear with everyone. Then the next question is, ram compression in turbojet involves. So you can see compression in turbojet involves, options are increasing speed of inlet air, compression of inlet air, reduction of speed of incoming air, and conversion of part of it into a pressure energy, or involves lost work. So compression process in a turbojet, it involves, what are the things it could involve? Any guesses?
Reduces the speed of incoming air and conversion of the.
Yes. So yes, that's correct. So turbojet, initially when you are having a turbojet engine, this inlet air will come in, and it eventually reduction of the speed of incoming air happens, and then this reduction of speed is what is converted into the pressure energy. So pressure energy is nothing but your compressor converts that into the pressure energy condition. So it's eventually converting that incoming air energy speed, that is the kinetic energy, it is converting into the pressure energy form. So that's what the compression in a turbojet it does. I hope that is clear. So now we have a question. So it's said, so we have an aircraft engine. It has an incoming air at a velocity of 280 meter per second. So I'll just write it down here. So you have an aircraft, and you have an incoming velocity CA at 280 meter per second, and the exhaust air, it goes at 650 meter per second. This is nothing but our CJ. Then they are asking us to find the propulsive efficiency of the aircraft. So the propulsive efficiency of the aircraft. So if you remember the equation, propulsive efficiency is nothing but 2 by 1 plus the change in the velocities, net ratio of velocities. So this is nothing but 2 by 1 plus Cj is nothing but 650, and Ca is nothing but the inlet velocity, that is 280. So eventually how much did anyone try?
Option is.
Yeah, so it comes nearly to 0.622, so approximately 0.6 you can take. So your option 0.6 is the correct. I hope this is clear with everyone. And yeah, so now we will move on to the 7th question. So a gas turbine engine has a dash overall efficiency and a dash mechanical efficiency than a reciprocating engine. So a gas turbine engine can it have a higher overall efficiency and lower mechanical efficiency, or it has a lower overall efficiency and a higher mechanical efficiency than reciprocating engine, or it has lower
B's.
Yeah, so it has both. B is the correct one. So a gas turbine engine will have a lower overall efficiency and compared to a mechanical compared to a reciprocating engine, whereas it will have a higher mechanical efficiency. So the mechanical efficiency will be very high compared to a reciprocating engine, because now you do in a reciprocating engine you had only piston that does all the things, and you have the air and you have everything. But now in a gas turbine engine you have separate components which does different works. So you have a higher mechanical efficiency than a reciprocating engine. So I hope that is clear. Yeah, so now next you have another question. So for a Brayton cycle, so we have discussed the Brayton cycle in the first session. So in a Brayton cycle with maximum work output having a cycle pressure ratio of 7. So you have a cycle pressure ratio, that is P2 by P1 is given as 7, and the compressor inlet temperature, so the compressor inlet temperature, that is T1, is mentioned as 310 Kelvin. Then the turbine inlet temperature will be, so they are asking about T3. What is the turbine inlet temperature condition? Now, has anyone tried? I think this similar question was there in your assignment also. Has anyone tried doing it?
C, sir. C.
Okay, so you are saying 942 Kelvin. So what equation you have tried to use? I hope that was Shankar. Okay, so you have this equation, that is for when you are having a isentropic process, you have an reversible adiabatic conditions, and you have this equation being satisfied there, PV raised to gamma constant, and if you rewrite this you will see that it is P2 by P1 is equal to T2 by T1 whole to the power gamma by gamma minus 1. So this is the relation between the pressure and the temperature. You can just directly use this equation and you can write P1 V with gamma equal to P2 V to the power gamma, and you can use the equation of state where density is nothing but P equal to rho RT, and rho is nothing but 1 by specific volume. So you can use this relation to get to this particular relation, and you can substitute. Now remaining all things are given. You have the pressure ratios being given, you have the temperature 310 Kelvin is given. Now gamma, so ratio of specific heats for, since whenever you should be careful when people ask this question, it is mentioned Brayton cycle. So the working fluid here is air. Here if you see the question, it is not explicitly mentioned that your working fluid is air, but it is said that it's for a Brayton cycle. So you should be aware that it's for air, and you should be choosing the ratio of specific heats gamma for air as 1.4. So it's more precisely it will be 1.414 or something, but you can choose 1.4 for now, and you can try to solve it. Now if you use this equation, but I think Sanskar, if you tried the equation, if you check the equation once more, there is some mistake in previous things and all, but actual equation when you are trying, it should be like gamma by gamma minus 1. So the actual answer should come close to 540 Kelvin. You can just check back, or if you have some issue.
540.
Yeah, so when you are putting it, so if you see the, now you see the values here, and you are asked to find the T2. So that is, so if you see the Brayton cycle, you had 2 to 3 as a combustion process, and you had 1 to 2 as your isentropic compression process. So now in TV diagram you will see like this: 1 to 2 you have an isentropic process, 2 to 3 you have an heat addition process. And now this process and this process, the exit at the inlet of the turbine is what is asked. That is, at the exit of the combustion chamber is what you have been asked. Now from T2 to T3 the temperature will increase, whereas from T1 to T2, here when you are seeing here in the question, it is mentioned the temperature at the compressor inlet is given. So T1 is given here. So when you are doing an isentropic process, it's an isentropic involves both adiabatic and reversible process. So isentropic is nothing but adiabatic plus reversible. So you can say the temperature over T1 to T2, here you will be having a change, and then using this relation you can directly find the value of temperature. So it is T2 by 310 Kelvin power 1.4 by 0.4, that is gamma minus 1, so 1.4 minus 1. So eventually T2 you will boil down to something like 540 Kelvin. So I hope that is clear. Now we'll move on to the next question. So the next question is, choose the correct order of the aircraft engines in the order of their increasing speeds. So the first option,
turbojet, ramjet.
yeah. So you have piston, turboprop, then turbojet, and then ramjet. This, as we discussed in the recent thing. So this order of the speeds, increasing speeds, is important when in any quizzes or anything when you are learning it. You should also be aware that why these kind of things, why this particular order is important, or how you are getting this particular order. When, because sometimes the question may be, now it is directly asked what is the increasing speeds. Sometimes it may be asked how it is the decreasing amount of air handling, what is the order, or you can be directly asked which is the one that is producing more thrust from this. In that order you need to rearrange that. So these are different ways. So you need to understand why this ramjet is having the highest speed compared to turbojet, and turbojet why it is having more than turbofan, and turbofan why it is having more than turboprop. So you should know the reason also, and at the same time you should also be aware that what are the altitudes or the ranges of speeds and altitudes at which these different engines work. Why turboprop you can't go to very high altitudes is a question that is generally asked. If you are coming into a PhD or an interview, you will be asked for these kind of questions. So this order, you learn it and learn how this order is coming also is important. And so we'll move on to the next question. So the ratio of flight speed to the exhaust velocity for maximum propulsive efficiencies. So it's ratio of flight speed, that is CA, to the exhaust velocity, that is CJ, or vice versa also it can be CJ by CA also. It is a ratio, it is mentioned for maximum propulsive efficiency. So it is asked for maximum propulsive efficiency. What is the ratio that is being asked?
This one?
Yeah. So this I think we have discussed recently. So when you are having your propulsive efficiency, that is 2 by 1 plus Cj by Ca, and here it is asked for maximum propulsive efficiency. So the maximum is for the propulsive efficiency. So efficiency maximum you can have is 100%. So this propulsive efficiency to be 1, then for at that condition the criteria that you need to mate is Cj equal to Ca. So the ratio between Cj and Ca will be equal to Cj by Ca will be equal to 1. So that's the ratio of flight speed to exhaust velocity. So I hope that is clear. And here, as Ramchandra has mentioned, however, this important thing is this is an hypothetical condition because you don't have thrust equal to 0. And one more important conclusion that can be drawn from this is that the high propulsive efficiency can be obtained by employing the jet speeds close to the flight speed. That's what it means. You don't need jet speed exactly equal to the flight speed. It needs to be very close for having a higher propulsive efficiency. Whereas for having a higher thrust can be obtained by increasing the flow rate of the air or the gas that is through the propulsive efficiency. So if you increase the Ca more, you will have higher thrust. And if you want to have a moderately or a sufficiently high propulsive efficiency, you need to bring your jet speeds very close to that of the aircraft speed, flight speed that you need to bring it up. So that's the conclusion that you draw. So this is a hypothetical case, but there are important conclusions that you can take out from this thing when you are having a propulsive efficiency maximum. Then the next question we have, in an ideal gas turbine cycle, the expansion in a turbine is represented by an isentropic process, an isenthalpic process, an isobaric process, or an isochoric process. So it's an ideal gas turbine cycle, it is asked. So are there any guesses? Anyone for an ideal gas turbine cycle? What is the expansion in a turbine is represented by an
Isentropic process.
Yeah, it's an isentropic process because in a compressor and turbine you have an isentropic process that is involved. Yeah, I hope from the gas Brayton cycle thing you know what are the different cycle values, or from 1 to 2 what it is, 1 to 3 what it is. That Brayton cycle is important, and in future lectures you will see that you have an ideal cycle, that is from 1 to 2 if you have an isentropic compression, and 2 to 3 to 4 that is from your combustion process. You will have an isentropic expansion, that is what is asked here. You have an isentropic expansion, but in reality getting an isentropic expansion is difficult. So in reality your curve will not go like this, instead you will have something like this, and your compression process will be like this. So this will be your 2 dash and this will be your 4 dash thing. So this is the, so here it is asked for ideal gas turbine cycle. So it was asked for this straight lines is what here it is been asked. When you are moving on to subsequent lectures, you will see there is an ideal gas turbine cycle and there is a real gas turbine cycle or actual gas turbine cycle. So there is a slight difference when you are looking into the question. Read carefully, is it mentioned an ideal gas turbine or an actual gas turbine cycle? So I hope that differentiation you will remember. And we will move on to the next question. So the next question is, gas turbines are suitable for aircraft propulsion because gas turbines are lightweight, gas turbines are compact in size, gas turbines have high power to weight ratio, or all of them. So which could be the reason?
High power to weight ratio.
Yes, gas turbines have high power to weight ratio, that is true. And gas turbines, aren't they compact in size? Because if your sizes are more, your range in weight will be more. So gas turbines, they are compact in size and they produce really large amount of energy, similar to the amount of energy that is produced in thermal power plant. In a compact size itself, they try to produce that much amount of energies. So this option also, gas turbines are compact in size, is also correct, and gas turbines are lightweight. That is also ensured for a commercial aircraft. The main source, the weight of the aircraft should be as low as possible, but safety and all should be considered. With all these things needs to be said, else if the aircraft is too heavy, you will need to consume lot more fuel for your aircraft to propel, and that will eventually lead to very high amount of cost of working and all. So gas turbines are light in weight, maximum possible with high safety and factor of safety they try to make it, but still they are light in weight compared to other engines, reciprocating engines and all. And gas turbine engines are compact in size, they are having high power to weight ratio. So high power to weight ratio means for a given weight the amount of power required to throttle is comparatively low, so that's why you are having a high power to weight ratio. And so eventually all the options are correct here when you are saying for a gas turbine, for specifically when you are concerned more towards aircraft propulsion. When you are gas turbines used for aircraft propulsion, if you are saying these all conditions are met. I hope that is clear. So next question we have is, why do the airplanes fly at higher altitudes during the long flights? So the options are to avoid collisions as they are at very high speed and controlling will be difficult if something like towers, hills comes in the way, or it is easy to communicate with the satellites at high altitudes, or to save the fuel as air at high altitudes exerts smaller drag force on the aircraft, or none of the above. So which could be the reason why airplanes are flying at higher altitudes? You might be seeing aircraft flying, but what could be
option
the
C?
Yeah, so option C is the correct one. So at higher altitudes you have the less drag, so lesser the drag, lesser the fuel you need to invest for your aircraft to throttle forward, so you need to save the fuel and you need at higher altitudes you move. That's correct. And so we are going with the last question. Yeah, what is the effect of increasing bypass ratio of a turbofan engine on its thrust? So bypass ratio, it is not introduced officially in the lectures, but bypass ratio I have mentioned. In turbofan you have the fan and some amount of air goes into the combustion chamber and goes out. Some goes without going into the combustion chamber, it goes as a cold flow and it generates the thrust. So it is asking what is the effect of increasing the bypass ratio. The thrust, it's not thrust, it is thrust. The thrust increases with increase in bypass ratio of a turbofan engine. The thrust decreases with increase in the bypass ratio of a turbofan. Thrust of the turbofan engine only depends upon the fuel rate, so no change of thrust with increase in bypass ratio, or we can't say will that increase or not.
Sir, option A.
Yeah, so thrust increases with increase in the bypass ratio of the turbofan engine, because for a turbofan engine the net thrust is nothing but thrust due to the propeller or the turbofan and the hot flow thrust. So these two add up in a turbofan engine, and that's why they are mostly used for all our commercial aircraft. They try to use these turbofan engines for getting thrust both from the fan and the inside combustion process. So I hope that is clear. Yeah, so I am done with the questions. So you guys have any question related to today's session or previous session, or any questions? Okay, so we have covered different components of the gas turbine power plants and gas turbine attachments, and we have seen introduction to the various aircraft engines, their engine performance parameters and all. So in detail we will solve if some certain parameters are given, what are the things that you need to be calculating once you know the cycle process and all, how to use the actual, what I mentioned, ideal Brayton cycle, and you have something called actual Brayton cycle. So how to use both of them, how will you use this ideal Brayton cycle as your reference to calculate the different processes in each of these stages. Components is very important, and that study of analysis is very critical when you are studying an aircraft propulsion. If you are given a turbofan engine or a complete engine, and if you are given certain parameters, that's what you can measure from an external perspective, or that's the parameters that you get in hand, then as an engineer, how you will design your engine, or how much pressure ratio, how many compressors you will be keeping, or what are the number of stages you will be trying to keep for a turbine, or how many compressor stages you will be installing to get to a particular pressure ratio. And all these things is what you will be dealing as an engineer. You need to know this. So that's what the subsequent lectures will help you to learn. So today we tried to cover the aircraft engine, and now the next week you will be learning about the ideal and real cycle analysis. Yeah, so
Sir,
yeah,
sir, PDF में शेयर करेंगे क्या ये?
sorry, previous.
सर PDF
Yes, PDF.
शेयर करेंगे क्या सर?
Yes, PDF. This video and this PDFs, I think you have received a mail from the online courses regarding a feedback form for the TH. Below that you have one more link for the Excel sheet. There is a link for the Excel sheet. If you click on that, so yesterday there was a session, and today's session and yesterday's session, all the Excel sheet links all the links to the PDF and the lecture. So these sessions are recorded. So all the links to these recorded lectures are also being provided there. So if you click on that link, it is shared with you, all the participants. It is shared. It is the second link, I think. Below the submit form, there is one more link for you to access the Excel sheet. In that you will get all this will be updated.
Okay, sir.
Yeah. Yeah. Any other? Okay. So if there are no more questions, so we are done for today. We will meet on next Saturday with the next lecture sessions. Thank you.
Thank you.